All right. Okay. That's officially 8:30, so that's an official good morning to you. And any questions? Let's see. How many people have registered already? All right. 66, so now I know how many people will be late. Well, this is our current topic. This slide summarizes everything we said yesterday about new physical quantities which most convenient to be used when we talk about collisions. This is basically a Newton's second law, but written differently in a different form. It's like the same person watched from a different perspective. And one physical quantity has a name impulse of a force, and that's a definition of that. It equals to a product of the average force acting on an object or on a system of objects. It's a very general law, like Newton's law is general, and times the duration of that action. And the second physical quantity is the momentum, linear momentum of an object. I'm just going to say momentum. It is equal to the product of mass and velocity, because velocity is a vector and mass is a scalar number. So this product has a direction, which means linear momentum has a direction. It's a vector. Same true for the impulse of the force. Now, we used to use little arrows to demonstrate that that physical quantity is a vector. People don't really use bars, horizontal bars in physics to demonstrate the word average. So this is the average force, net force equals to mass times average acceleration. This is the expression for the average acceleration, final velocity minus initial velocity divided by time. So we just keep in mind that the force in the definition of the impulse of the force represents the average value if the force changes. So we got to figure out how to get the average. And as we said, we have two extreme situations. Number one, when impulse equals 0. In that case, momentum of an object or of the whole system doesn't change. And number two, when the impulse is not equal to 0. In that case, it changes linear momentum. Well, that was the last slide we saw yesterday. We got to talk about how to make an estimation for the impulse of the force when the force changes in time. On the left, we see a picture for the constant force. Constant force, Constant force. Same at this instant, the same at this instant. So in this situation, if we want to calculate the impulse, we just have to multiply this value of the force, because when the force is constant, the actual value of the force and the average value of the force, same things, times the duration of this action. That's it. And from geometry, we know that if you multiply these two numbers, in geometry, this is length times height or times width, that is equal to the area under this line. And this gives us a hint how can we approach a situation when the force changes in time. Something like this, wherever. This is actually a situation when a ball collides with the wall. When the ball starts touching the wall, the force starts from 0, and then it increases to some maximum value. And when the ball leaving the wall, the force goes back to 0 again. But since we know how to calculate the impulse for the constant force, what we have to do is just break this whole time interval into many, many, many tiny time intervals. Within each time interval, we can consider force almost constant. So then we would have to calculate the tiny impulse of the force for each individual time interval. And for each individual time interval, the impulse would have been equal to the area of this little vertical rectangle. And for the next tiny time interval, the impulse would be equal to the area of the next, and then the next, and then the next, and then the next vertical rectangle. So in the end, we would have to just add them up all together to get the total impulse of the force. But geometrically, that addition would lead to the whole area under this line. In physics, we call it integration, but that's PY105 because that's our course is not the calculus-based course. But we don't need calculus. We can see the area. That's it. That's all we need. So this area represents the impulse of the force acting between, well, time number 1 and time number 2. Now, if we want to, we can actually use this area to calculate the average force, because the average force will be just equal to the ratio of the impulse divided by the time interval. The average force, F average, normally has a value some between the minimum and the maximum values of the changing force. So since we have devices which can measure things, for example, a force sensor measures force acting on a cart, we can use this approach to measure the impulse of the force acting on a cart when it collides with another cart. And you will do that next week in the next lab. Well, now you can understand what you're looking at. Let's just use an example of this approach. In this problem, we need to calculate the final velocity of an object which was under influence of changing force. Well, the force here was changing kind of easily, in an easy manner. It was increasing, then it remained constant, then it was decreasing. But now we know what to do, because if you want to calculate the final velocity, velocity, what is it related to? Well, our experience tells us velocity might be related to acceleration, time, displacement. But now we also know it might be related to a linear momentum. So we got to focus on our knowledge and choose what connection probably would be, well, the most convenient to choose, to use, and try it out. So momentum is related to the impulse of the force, and the impulse of the force is related to area. So this type of relationships kind of guides us that first we have to calculate the area that will give us the value of the impulse, and now we can write that mathematical relationship. This little map only represents the fact of the connections. They are connected. Now, how? That answer is answered by a specific equation. Yeah. Impulse momentum theorem. Well, this consideration gives an idea of what to do, and now we just have to try it. So, the impulse of the force equals area under this line, and we can break it into 4 different parts. We can see it because we have eyes. 1, 2, 3, 4. So what we have to do is calculate area number 1, area number 2, area number 3, area number 4. Not area number 9. So now we got to use geometry. For example, this area is the area of what shape? Does it look like a circle? No. Does it look like a triangle? No. How does it look like? Like what? Trapezoid. So we got to go back in time, I don't know, grade 8, 8th grade, and find the equation for the area of a trapezoid. Of course, you could also break it down into 2 additional elements, but that would take extra time. So area number 1. So this base equals 3, this equals 6, the height equals 4. So 1/2, 3 plus 6 times 4. Area number 2 is equal to 9 minus 4 times 4. Length times width or height. Now, area number 3 is the area of a triangle. So 1/2 base times height. Base is 10 minus 9, and height is 4 again. And area number 4, that's kind of tricky because it's below the x-axis. So what does it mean? Well, physically it means force changed its direction to the opposite, and force has a direction. So mathematically it means we have to treat this area as a negative number. And how do we calculate again? It's a triangle, so 1/2 times base, 12 minus 10, times 8. Or we could write it 1/2 times 12 minus 10 times negative 8. Would have been exactly the same result, so we could just use the actual value of the force. So whatever reasoning we use, we get the same result. Now what we have to do? Now we have to add them up again. I'm not going to do that. I just write this again. What it should be equal to? It should be equal to final momentum minus initial momentum. What are we looking for? We're looking for the final velocity. Final velocity equals final momentum divided by the mass. And that's supposed to be equal to now initial momentum plus the impulse over mass. So the only tricky part left is calculating the initial momentum. We know the speed, which is 4, but also we have to account for the fact it was traveling to the left. So what does it mean? The initial velocity has a negative component. So to calculate the initial momentum, we have to multiply mass and the initial velocity, which is -4. So we have to remember the difference between speed and velocity. Speed is the absolute value, magnitude of instantaneous velocity. Well, and yeah, we know the mass, that's it. -4 plus wherever it is for the impulse divided by 3. That's the answer. All we have to do is just calculate the actual value for each area, add them up. That's simple. Any questions? Yes? Yes? No, I didn't. In this case, I didn't. I could have, but I got my coffee before. What happened to it? That's a good question. What happened to the mass? Here. What happened? What happened? Yes, it got cancelled. Questions, please? You have a question? Not to me. Okay, moving on. So, you don't know yet what I will ask you, so just get ready. You don't know the terminology. The terminology in physics is simple. You have two objects. One object, one object bounces off the surface. Second, no, nothing. So when object bounces, we call it happy. And naturally, that's what we call sad. But the question is about so-called decision balls. People who cannot make a decision, they use these balls. Sad, happy. So you take randomly, do I have to go to the class today? No. Do I have to go to the lab today? Yes. So the experiment looks like this. We get the sad ball, doesn't bounce. Nothing. We get the happy ball. So the question, which of these balls, sad or happy, exerts stronger force on this wooden brick? That's not a tricky question. This is just to stir a conversation, right? Because it's not a tricky question, I would expect that for this particular question, we would have 100% correct answers. You see, it was 66, now it's 82. So 82 minus 66, 16, right? But only 6 people said they were late. Okay, number 2. So if you said that the happy ball exerts stronger force, you're right, because we can see. If you said something different, ask yourself, why? Of course, we can see that the ball which didn't bounce didn't exert force strong enough to knock it down. But what is physics behind this? Well, physics is actually very important. Yesterday we have solved the problem already with the ball bouncing off a ball. This is what we call happy. Yeah. So I just want to very quickly refresh the reasoning. Initial velocity points to the left. Final velocity points to the right. If we want to calculate force, we have to calculate, well, change in the momentum over time. That's how Newton wrote it. And in this situation, that's going to be momentum final minus momentum initial over time, mv final minus m and the magnitude of V initial, like this is how I want to write it, with the minus because it's negative over time, and because the collision is ideal, we can just use the same variable for both magnitudes. That gives mv minus mv over 2, over delta t, sorry, I already think ahead. So 2 mv over delta t. That's an expression for the happy ball. What will be the difference for the sad one? For the sad one, it doesn't bounce back. So it sticks to the wall, which means final velocity will be equal to what number? 0. So if we repeat exactly the same calculation, it's got to be 0 minus minus plus mv over delta t. So we can see that the difference between the force they exert is a coefficient of 2. The happy ball exerts force twice stronger. And that works for any situation when an object is bounced or not bounced off a surface. For example, calculation, for example, of a mirror. So if you have a shiny mirror, light exerts force twice stronger than if you had a black mirror. And this idea is behind the idea for traveling in space. If you have a very, very huge solar sail, it has to be shiny. It cannot be dark. But we will use the same reasoning in the future when we're going to talk about molecular motion, because every molecule can be considered as a first approximation as a tiny ball which hits the wall. And when that tiny ball hits the wall, it bounces back. So it exerts a force on the wall. But if many, many billions of molecules hit the wall simultaneously, the force is strong enough to actually exert a significant pressure. For example, atmospheric pressure is very, very high. And that's how they make it, just by bouncing on everything around. Tiny, tiny particles. And if we use this type of reasoning, we can actually calculate how atmospheric pressure is related to the volume of the room and the temperature, which is kind of neat. Well, that's not a new information on this slide. We saw it before. We know that when net force acting on an object or on a system is equal to 0, the total linear momentum of the system should remain constant, remain conserved, remain the same, no matter what is happening inside the system. And a very common situation involves two objects, maybe more, but we limit ourselves by only two objects, like these cards, for example. So first we neglect friction. If we neglect friction, gravity and normal cancel each out. Gravity and normal cancel each out. Internal forces don't change. Remember, I don't have a sail, but you should remember, a cart with a sail, internal forces do not change behavior of the system. So this is a typical situation when we can assume net force equals 0. Even if it's not 0 sometimes, if collision happening very quickly, the impulse of the force still is practically 0. So in all those cases, we can assume that the total linear momentum remains constant. Constant means the same before and after the collision. So what kind of collisions we have? Well, that's the law for two objects. If we have two objects the total linear momentum of a system has to be equal to the sum of individual linear momenta. And this sum should remain constant. This sum should be the same before and after the collision. So we can use F and F to demonstrate final or after the collision state, I and I, initial or before the collision. And interestingly, we talk about collisions. And the first law we have to use to analyze any type of a collision is the law of conservation of linear momentum. But to classify possible collisions, we use energy. These are all types of collisions, well, known in general. What might happen to kinetic energy? Well, first of all, nothing. If we neglect friction, any kind of friction, mechanical energy should be conserved. And that type of a collision has a name, elastic collision. But years ago, people called it absolutely elastic collision, even if the word absolutely not necessarily, you know. I like to call it absolutely. I'm old. Now, what else might happen? Well, these two cards might move together after the collision. They stick to each other and form one object. This type of a collision has a name, absolutely inelastic collision. In general, what might happen is, well, something like this. And if we cannot neglect friction, energy changes. We call it just inelastic collision. And also, what might happen is something like this. No. So, something like this. Well, we call it collision. Also, it looks like more like explosion. In that case, we call it superelastic collision. In this situation, we, during the collision system, get extra energy. So the final energy is greater than the initial energy because of, well, spring or, you know, piston. So these are all possible situations. Nothing else might happen. And for every situation, we can write the law of conservation of linear momentum. Now, when we write the expression for a linear momentum, we have to know what each subscript means. For example, 1 and 2. That usually means object number 1 and object number 2. Initial, final, that usually means before and after the collision. So this represents the linear momentum of the first object after the collision. But this variable, P2y, represents the linear momentum of the second object, but before the collision. So we have to be able to read those symbols. And of course, we talk about one-dimensional motion. Positive x direction points to the right. Velocity is a vector, as every velocity always can have positive or negative component, or sometimes zero. So we have to keep in mind that all these velocities, all those numbers, represent an actual component which might point, which might be negative or positive, depending on how velocity points. Velocity points to the right, component is positive. Velocity points to the left, component is negative. The tricky part is, until we have solved the problem, we actually don't know how would the card move. So if we don't know if it's going to move to the left or to the right after the collision, how do we assign the velocity to it? Anyhow, which means the most convenient choice pointed to the right, and solve the problem. And if your number becomes positive, that means it travels to the right. Indeed, as you guessed, hypothesized. But if you assumed it will be traveling to the right, and your calculation gave you a negative number, that means your assumption was wrong. You have to correct it. In reality, it travels to the left. Very simple. Well, of course, we're going to do examples, but first the question. A special case, this is absolutely inelastic collision, which means these two cards form one object. So they have the same mass, and the hardest part for me is to make them move at the same speed. You cannot do it without PhD. So that's the experiment. That's the question for you to answer. The question is about mechanical energy. What do you think happened, if anything, to mechanical energy in this collision? You can look again. Question number 3. Well, so far we have a 50-50 distribution. Well, let's think it through. That's a problem about a specific physical quantity. In this situation, mechanical energy. If we talk about mechanical energy, what do we have to do first? First, action. We cannot solve problems just by thinking. We have to act. That's the only way to solve problems. So, what action should I do right now? I'm listening. No? Good guess, but for this situation, if we talk about mechanical energy, what should I do first? Write the equation which represents what? If we talk about mechanical energy, why would I write an equation for work? I have to write an equation for what? If we talk about mechanical energy, why do I write equation for friction? If we talk about mechanical energy, what should I write first? Well, that's better. That already has the word energy in it. But if we talk about mechanical energy, what should I write first? Gentlemen. Yeah, the last gentleman in the room. Yeah. What do you think? If we talk about mechanical energy, we need to analyze what's happening to mechanical energy. My first action should be what? Someone say something. Keep saying. Okay, so you want me to write that mechanical energy is equal to kinetic energy plus potential energy. Now, because it's an equation in physics, like every equation in physics, it has a name. What is it? And in physics, every equation is either a law or a definition, and nothing else basically exists in physics. Laws and definitions, well, sometimes we can derive some more equations, but the fundamental equations are either laws and definitions. What is this? No. A definition of mechanical energy. That's what it is. So if we talk about mechanical energy, the first action is to write what? The definition of mechanical energy. That's it. That's the answer to this question. That's the first action. Now, we can write this definition twice. First time for the situation before the collision, we call it initial. Second time for the situation after the collision, because that's what we need to compare to figure out, is there any change or not? And mechanical energy of this system before the collision includes kinetic energy of the first cart before the collision, potential energy of the first cart before the collision, kinetic energy of the second cart before the collision, potential energy of the second cart before the collision. And please, please, don't confuse collision and collusion. So, what about potential energy? What type of potential energy do we have in this situation? Has a name, like everything else in physics. You know, if you would forget the names of your friends, they would hate you. Same works with physics. Trust me. So, what type of potential energy is used here in this situation? Gravitational, okay. And if we want to write an expression for the gravitational potential energy, we need the vertical axis, and we have to choose the origin, the zero level. Where can we choose the origin? Anywhere. Where do you want to choose it? Okay, if this is a horizontal situation, everything happening horizontally, so what would be the lowest point? Ground level, so 0. And that makes potential energy automatically to be equal to 0. It will not matter, because it's the same before and after. And now, same mass, same speed, squared over 2. Same mass, same speed, squared over 2. So this gives us mv squared. The expression for initial kinetic energy of this system. Now, you have to look at the experiment. I'm going to do my best to make sure the speed is the same for both again. What is the speed of these carts now? 0. So we can write immediately mechanical energy of the whole system after the collision is 0. No potential, no kinetic. So it was mv squared, now it is 0. Did it change? That's yes or no question. Yeah? It did change. It changed. There is no mechanical energy left. Where did it go? That's a different question. That's friction. Friction changes mechanical energy. So it went into, well, eventually heat. If I ask you, in this experiment, mechanical energy conserved, the answer is no. Mechanical energy is not conserved. Energy, of course, always conserved. It getting transferred from kinetic to heat in this experiment. This is the type of reasoning we have to use every time when we need to answer a question related to energy. That's an example of that type of reasoning. All steps of the strategy have been shown. Use it if you need to figure out something about energy. Well, again, let's do a specific example. Here, we know the masses and the speeds of the cars before the collision. And this is, again, the absolutely inelastic collision, which means they form one object and travel together. All we have to do now is to apply the law of conservation of linear momentum literally, straightforwardly. System initial, linear momentum of a system initial should be equal to the linear momentum of the system final. Linear momentum of a system equals linear momentum of the first cart initial plus linear momentum of a second cart initial should be equal to linear momentum of the first cart final plus linear momentum of the second cart final. Each momentum equals mass times velocity. So I will start writing expressions for each linear momentum. Mass of the first cart times, well, I choose my positive x direction to the right, and I write components. So the x component of the initial velocity of the first cart, mass of the second cart times the x component of initial velocity of the second cart, mass number 1 times the x component of final velocity of the first cart plus mass number 2 times the x component of the final velocity of the second cart. Now we can start throwing numbers in. And I'm not going to say that. I'm just going to write it down. Well, I'm going to say that. I lied. 2 times 2 plus 0.4 times, what should I write? Minus negative 1 minus 1. Because this velocity, which is initial velocity of the second cart, points to the left, should be equal to 2 times V1fx plus 0.4 times V2fx. Now we have to say something very, very important, very, very specific about this collision. If they form one object, if they travel together after the collision as one whole object, what does it mean? Velocity has to be the same. It's the same number for both. If it's the same number for both, we actually don't have to write all those subscripts. Let's just write u. So I can continue my calculation over here. 2 times 2 is 4, minus 0.4 should be equal to 2 times u plus 0.4 times same u. So that gives me 3.6 divided by, that's a u, not a 4, times divided by 2.4. That's it. So this type of a collision, absolutely inelastic collision, is the easiest case which might happen. When they form an object, one object after the collision, that means they travel with the same velocity. It might look initially that we have one equation and 2 unknowns, but no, that's the same number, so only one unknown. Any questions? All right, so that's the answer. Now, we just said that in this situation, the energy should change because in order to keep them together, some kind of internal friction should work, and friction always decreases energy. So if we want to find out how much energy was lost to friction, all we have to do is just repeat the same type of reasoning. Kinetic energy of the first card before the collision should be equal to 2 times 2 squared over 2. Kinetic energy of the second card before the collision should be equal to 0.4 times 1 squared over 2. But kinetic energy of the both cards, because they travel together, just final, should be equal to total mass, which is 2 plus 0.4 times the speed we found, 1.5 squared divided by 2. That's it. So we can compare the energies before and after. Oh, I had a slide for that. All right. Turns out it's going to be negative 1.5 joules. That's how much energy was left to, was lost to friction between the cards. Moving on. Now, there are many similar situations which can be solved with the exactly same type of reasoning, but kind of backwards. We already said that an explosion looks like this. You had initially a system, and it's broken into different parts traveling away from each other. And the nature of those parts don't matter. Could have been two persons pushing on each other, someone jumping off a cart, and the cart travels in opposite direction, an actual explosion, a shot. So all these situations physically identical. It's basically collision backwards. So for all of these situations, the straightforward application of a law of conservation of linear momentum immediately gives the answer. Now, remember this card. This was a demonstration of Newton's third law. The fan pushes on air, the air pushes on the fan, and they travel together. But there is a difference between a situation like this and, let's say, a situation like that. We call it a rocket. Yeah. What is the difference? If we seal up the room, suck out all the air, and turn on the fan, what's going to happen? We will not know. We will die, right? If the fan needs air, the medium. In vacuum, it's not going to work. However, the same law, Newton's third law, tells us that we don't have to have medium. I could, well, why do I need this? Because it's heavy. This thing is so light, so if I just let it fly, it would fly like a bullet. It might damage if it hits someone. So that's why I need this. But I could put it vertically, give some more speed, and that's how we get into space. So what is physics behind this? Well, basically, it's again a law of conservation of linear momentum. You have two parts of a system, gases, which travel in one direction, and a rocket, which travels in another direction. Initially, linear momentum is conserved. Zero. But if I let the air fly out, that means to keep the whole momentum zero, this balloon should travel, oops, you can keep it, in opposite direction. So the Newton's third law, in a way, is a representation of a law of conservation of linear momentum, or vice versa, we can say. The law of conservation of linear momentum, in a way, is a representation of Newton's third law. And if you do some mathematics, you can calculate how much fuel you need to store in a shuttle in order to make it reach the outer space. All based on this kind of simple physics. Now we're going to talk about different situation. Elastic collision. This word elastic for me means absolutely elastic, and the word absolutely means no friction. It's just a helpful mnemonic device for me. Elastic means absolutely elastic, means no friction. If there is no friction, mechanical energy has to conserve. So, which means we can write two equations. And when we have two equations, we can solve it for two unknowns. So let's do it. This is a good mathematical exercise. So we have two objects. Colliding with each other. No friction. Mechanical energy has to be conserved. So after the collision, they travel separately. Why did I point all velocities to the right? That makes mathematics easier, just convenience. But in reality, it doesn't matter, because each velocity has a positive or negative component based on the direction, and we always can figure out when the number has to be positive or negative. Plus, that situation, that type of a collision is not impossible. It's just the cart behind should travel faster and eventually reach the cart in front of it. Something like this. No, not like this. Something like this. Collision. Of course, if the cart in front of the second cart would travel faster, collision would never happen. So first, of course, we have to write the law of conservation of linear momentum, M1. And when I write V1, I mean V1x, the x component. I just don't want to write that letter x so many times. I keep it in my mind. This is a component of the velocity of the first cart before the collision, M2, V2. V2 represents the x component of the velocity of the second cart before the collision. And for velocities after the collision, I use a different letter, again, to avoid writing additional subscripts. So M1, U1 plus M2, U2. And I have to keep in mind the exact meaning of each variable. U1 represents the velocity of the first cart after the collision, well, relative to the x-axis. U2 represents the x component of velocity of the second cart after the collision. And that's it. That's all I can write for now. Well, we make a general assumption that we know the initial velocities, and we're looking for final velocities. Mathematically, it's absolutely irrelevant. Yeah, as long as we know any two velocities, we can calculate any other two velocities. We assume we know masses. But now we have to write a second equation. Yeah. And the second equation is the law of conservation of mechanical energy. And again, for the mechanical energy, we set potential energy to 0 because everything is happening horizontally. So only kinetic energy matters. And that's all we can write down. Now, of course, we can write physics is done. problem is the second equation is quadratic equation. So there are two ways to think about it. Number one, straightforwardly solve the first equation for the first unknown, let's say for u1. u1 will be equal to m1 v1 plus m2 v2 minus m2 u2 divided by m1. That's already a very complicated expression. And then you can plug in this expression into the first term. That will give you a very, very complicated quadratic equation, which is doable. But there is a way around it, algebraical way, so yeah, brace yourself. First, we can cancel. Well, the idea is always take the most complicated equation, try to make it simpler. And the quadratic equation is more complicated than the linear equation, so we want to make it simpler. And to make it simpler, we want to rewrite it. First, we cancel all 2's, and I want to collect everything related to card number 1 on one side, everything related to card number 2 on another side. m1 v1 squared minus m1 u1 squared equals m2 u2 squared minus m2 v2 squared. You don't have to write it down. You can find it online. It's a standard calculation. On the left, m1 is a common factor. On the right, m2 is a common factor. Now, again, we have to go back in time. I don't know, 8th grade, my favorite grade. And refresh our memory. This expression has a name, the difference of squares. It can be written as a product. As a product of what? You say something. I see you move your lips. A minus b times what? A plus b. How do you prove it? Well, you just cross multiply everything. 8 times a squared, b times b, b squared, and a times b minus b times a cancel each other out. But what we see here is exactly the same structure, m1 times, and here we see the difference of the squares. It's going to be equal to v1 minus u1 times v1 plus u1. And that should be equal to m2 times u2 minus v2 times u2 plus v2. And now we should get a feeling. Probably it's a time to go back to the first equation, because first equation also relates just masses and velocities. Again, if I collect everything related to card number 1 on the left and everything related to card number 2 on the right, what do I have? m1 v1 minus m1 u1 equals m2 u2 minus m2 v2. And again, masses represent common factors in each expression. And now if I compare two expressions, this one and this one, I can see the exactly same terms. And now if I compare these two expressions, I can see the exactly same terms. So, well, technically, as long as they don't equal to 0, we can cancel them out. We can cross them out. What's left? v1 plus u1 equals, well, I want to flip the order, v2 plus u2. This is easier to remember. So we have proved that instead of using a quadratic equation, we can use a simple linear equation for this pair of equations. So what's next? Yeah, well, I got it here. All right. So for every elastic collision, or I like say absolutely elastic collision, these are equations we can always use. And these equations are simple to solve, linear equations. And of course, you don't have to do all that calculation every time. Oops, wrong direction. You don't have to do it. I do it because I like it. That's the only reason. All you can do is just remember that instead of using the law of conservation mechanical energy, you can use this equation, which also has no name, but only when mechanical energy is conserved. No friction is involved. All right, we got to do some example. So what do we have here? Let's just plug the numbers in. From the picture, I can see the masses and the initial velocities. So 2 times 2 plus 2 times 0 should be equal to, well, we don't know final velocities, so 2 times u1 plus same as 2 times u2. That's a special case when both objects have the same mass and second object is initially at rest. And now I can write the second equation, this one, right here. 2 plus unknown, oh, yes, that's after, equals the second unknown velocity plus 0. So this action doesn't require any thinking. We just have to pick the right numbers and plug those numbers in the right places. Physics is done. Well, let's see what we can do about it mathematically. First of all, I wouldn't multiply 2 times 2, make it 4. I would cancel these 2's, and that's 0. So what I have is 2 equals u1 plus u2. On the other hand, 2 plus u1 equals u2. So if I replace u2 in the first equation with 2 plus u1, I have 2 equals u1 plus 2 plus u1. That makes an equation look very easy. u1 equals 0. What does u1 represent? We have to be able to say it in words. That's physics. u1 represents the velocity of the first cart after the collision. The velocity of the first cart after the collision has to become 0, which means the first cart should stop after the collision in this experiment. How do I do it? Do I do it this way? No. Friction. I have to do it this way. Magnetic repulsion. So one cart is initially at rest, and second hits it and stops, according to the theory. If you ever play pool, that's a hard shot. That's how you make the cue ball stop. Of course, if you don't spin it. Well, any questions? the general theory, the specific example. I've got a demonstration, and I have a question about it. You don't know the question yet, so don't answer. First, I want to show the demonstration. This device has a name, a ballistic pendulum, and a device like that actually has been used to measure how fast a bullet flies when it's shot out of the rifle. See, when the pendulum is deflected, this device holds it still. So now we can take a protractor, measure this angle, and then we can deduce information about the speed of this bullet. So this is a typical experiment. Shot, and it's stuck here. And of course, when this pendulum moves up, the gravitational potential energy, mgy, increases. And now kinetic energy is 0 because nothing is moving. But the ball was shot, there's a spring, I compress the spring, and when I compress the spring, I actually store some energy in it, and now I release that energy, it will fly with a certain speed. And now we want to use this experiment to calculate the height. So what we know is the mass of the bullet. 10 grams have to be converted into kilograms. We know the initial speed of the bullet, 100 meters per second. We know that this pendulum has the mass of, I'm going to use a big M, capital M, 990 grams, which is 0.99 kilograms. So what we want to relate is kinetic energy initial, which only stored in the moving bullet, equals 0.01 times speed squared over 2. That's going to be what? 0.01 100 and 150. You have to check 50 joules. And when the bullet is stuck inside the pendulum, they form one object with total mass. I have no M left. All right, M total will be equal to 0.99 plus 0.01, which is 1 kilogram. And the energy of this pendulum, that's a potential energy. Let's calculate it above the ground, which will be equal to mgy, or 1 kilogram times 10 times height we are looking for. And now that's final potential energy. Now the energy getting transferred, so 50 should be equal to 10 times h. H equals 50 over 10, 5 meters. Now I'm asking you a question. You have to choose between yes, that was a completely correct calculation. Mr. V again correct. Or you can say no, that's a wrong calculation. As usual, Mr. V made a mistake. That's not about mathematics, that's about physics of this particular situation. So please enter your choice. Because when I come back, I will ask you to use your hands to show me what did you choose, because I have a follow-up question. So if you agreed, please raise your hand. If you disagreed, if you say this calculation is wrong, please raise your hand. Now, if you say that I'm wrong, you have to prove it. Unless you can prove it, unless you can explain what went wrong, that's just a hunch, a guess, not reasoning. So, you said I'm wrong. What did I do wrong? You cannot start a sentence in physics from I feel.
Is there an X component?
No, it's not about mathematics. It's not about X components. It's about physics of this phenomenon. Let me show you one more time. It's not about math. It's about this ball being held inside this pendulum catcher. Yes? Because energy is conserved? Yes? And if that's kind of inelastic collision, what specific force holds it inside this pendulum? Friction. There is a force of friction. Without friction, it would slide out. It wouldn't be caught. Only friction holds it. When friction is acting, mechanical energy cannot be conserved. Did I use anything related to friction in my calculation? No. So that's what is wrong. What I wrote mathematically looked like this. This is the law of conservation of mechanical energy without friction. What I should have, so that's wrong. What I should have right is this: kinetic energy plus work done by friction should be equal to wherever it is. Yeah, that's it. This term makes difference. I didn't use it. I don't actually know it. First, I need to figure out how to solve the problem, how to find that height, then calculate potential energy, and then I can subtract potential energy from kinetic energy, and then I will know how much work friction did. So we still have to solve the problem first. Well, let's do it. The idea was absolutely correct. We just have to consider the whole process as, well, several processes happening one after another. And the most important part, which was missing here, is a collision, not collusion. The ball and the catcher, just before the collision, were separate, and then they started moving together. That's the absolutely inelastic collision. That's it. So at first, we have to solve a problem about collision. And then, after that, they start traveling together. And we can, after that, when the pendulum swings up, there is no friction. We can apply the law of conservation of mechanical energy without friction. Before doing that, I want to show one more experiment, similar to one of your, well, actually two of your homework problems. Imagine this is a wooden block. Okay. I just have to check it works. It works. It's So that's a bullet. What's going to happen? First, we observe a collision. Only this situation absolutely inelastic collision, because after the collision they start traveling as one object. But then it was sliding before it stops. So after the collision, until it stops, the process has nothing to do to collision anymore. That process is related to change in the energy. And we have solved the exactly same problem before about the sliding box. So when we have solved the problem about box, we made it move by giving a push. But in this situation, we made it move by shooting at it. But again, after the collision happened, it doesn't matter anymore what was the reason for this object starting to move. It's all about energy after the collision. Well, so what kind of a collision? We just said absolutely inelastic collision. I'm not going to ask this question. That's the answer. So that is a wrong way to calculate the unknown height. What is the right way? Well, again, since we break this problem into two parts, the first part, collision. And for the collision, we have to start from the law of conservation of linear momentum. The mass of the bullet times the velocity of the bullet plus 0, because the pendulum was not moving, should be equal to the mass of the bullet plus the mass of the pendulum together, times, well, the velocity of them right after the collision. And then, right after the collision, having this velocity, the pendulum swings. So now, so this is the law of conservation of linear momentum. And now we can write the law of conservation of mechanical energy. And in this situation, again, we can write that kinetic energy of the catcher with the bullet supposed to be equal to final potential energy P pendulum mgh of the catcher with the bullet. That's it. So now we can, so physics is done. I need some kind of a stamp with this. So mathematics is trivial. You just plug numbers, calculate u, and then you can use this u to calculate h. In your homework problem, you do it backwards. First, you have to use the law of conservation of mechanical energy, and then you have to use the law of conservation of linear momentum, because in a homework problem, that's what you're looking for, the initial velocity of the bullet. So, readable slide, and the actual answer. The actual answer is not 5 meters, but only 5 centimeters. That's how much friction, how much work friction does. Any questions? Well, so I did that experiment already. And the last example related to a two-dimensional collision. I have an example of that. So, almost no friction. No, kind of. So this is one-dimensional collision. Two-dimensional collision looks like this. So they travel, well, not necessarily at 90 degrees, but after the collision, they may travel theoretically in any possible direction. This is kind of elastic collision, but we will solve a problem about absolutely inelastic collision when two pucks in this situation collide, stick together, and travel as one whole object. Of course, because it is a collision, we have to start from law of conservation of linear momentum. But sometimes it is easier actually using momenta, not velocities. Why? Because we know how to add vectors. So the smaller puck has momentum of mass times 3 meters per second. I want to write it like this, to make a point. Again, as in physics, when you write a letter, it's very important that you know what it means. Because this m represents mass. This m represents what? Meters. If you forget, you multiply, you get meters times mass squared, which doesn't make any sense. So this is P1 initial, this arrow. And this arrow represents double mass times 2 meters per second, and that is P2 initial. And now what we need to do is just add two vectors, this plus this. How do we add vectors? By using a tail to a head rule. If this is P1 initial and this is P2 initial, that should be P total initial. On the other hand, because of the law of conservation of a linear momentum, that also should be equal to P total final, the same arrow. So how can I calculate the magnitude of final momentum of the whole system? Because they travel together, they have the same velocities. So it should be equal to, according to Pythagorean theorem, P1 initial squared plus P2 initial squared. In my calculation, P1 equals m times 3 squared, and P2 initial equals, well, I write it again in the same way, 2 times m times 2 squared. So that gives me square root of m squared times 9 plus m squared times 16. We know how to do the mathematics. M squared is a common factor, and square root of square is just m. And what's left inside is 9 times 16, 25, which is a very convenient number. So that gives me m times 5. But that's not the speed. That's not the speed we're looking for. That's the momentum. However, if we knew the speed, that final momentum would have been equal to total mass, which is little m plus a big M, times that final speed we are looking for. So the final momentum should be equal to 3m times v. On another hand, we just proved it also equal to m times 5. And now we can calculate that speed. This is again an example, a situation when we don't know some values, but we don't need to, turns out. The final speed will be equal to 5 over 3 meters per second. This is an example of a two-dimensional collision. And of course, if we need to calculate the direction of the motion of these two objects after the collision, all we have to use is the right triangle, calculate this angle theta. From this triangle, tangent of theta will be equal to the ratio of initial momentum of a second puck over initial momentum of the first puck. Now, we talk about a system, and a system again and again and again, and we know that a system represents wherever we want it to be. In particular, two cards. But sometimes when we look at the system, we don't really care what's happening within the system. Only we care how it moves as a whole. And in that case, we don't really need to know how individual parts move. But we need a special location, a special point, which describes the motion of a system as a whole. So we have invented a way to find that point. If we look at the system, we start moving away from it. We know eventually we will not be able to see the difference in size. It will become just a little dot. And that little dot will move in space in a certain way. And that little dot, which describes the motion of a system as a whole, has a name, center of mass. So, common sense tells us if you have two identical parts of a system, center of mass should be in the middle because of the symmetry. If you have something like this, that little dot, which moves as a whole, will be closer to a heavy object. And when we look at the center of mass, it will move according to the equation for It will move according to equation for a point-like object. So this is the center of mass of this system. This is a system. And if I toss it, it will spin and fly. But the center of mass will move exactly like just a little ball. That's why using center of mass is convenient. When we don't care about the motion of individual parts, all we have to look at the motion of center of mass. And, well, you will not be able probably to see it, but try to see this LED will move as a standard projectile, like this. All right. I almost killed my computer. So, see, this is the center of mass here, because this end is heavier. But, again, if I toss it, these LEDs will move just like a standard projectile. Okay. Every time I'm almost have a heart attack. All right, let's try one more time. All right. The equation for the center of mass we will discuss tomorrow.
switch.